Next we start exercises on well-ordered sets. Let's see this second one. In part A, we have to show that in any well-ordered set, every element except the largest element, if it exists, has an immediate successor. The well-ordered set may not have a largest element. Even if it does, except that element, the other elements all have immediate successors. So that is part A. And in part B, we have to find a set in which every element has an immediate successor, but the set is not well ordered. It is an ordered set, but in spite of every element having an immediate successor, the set is not well ordered. So let's see the solution. Okay, so this is the solution. Let A be a well ordered set and let small a be an element of capital A. Capital A may or may not have a largest element, but even if it does, small a is not that largest element. It is some element. Then what we do, we consider this subset B consisting of those elements of A which exceed small a. Because small a is not the largest element, there will be at least one such x in A which is greater than small a, and that makes B non-empty. And clearly B is a subset of A. So B is a non-empty subset of A. And because A is well ordered, so B will have a smallest element which we denote by minimum of B. And this minimum of B, of course, will be the immediate successor of A. Exactly how, you have to go through a little argument to show that this minimum really is the immediate successor of A. That I leave to you. Okay, so that way we get the immediate successor of any element of A other than the largest element. And then in part B, we have to find an ordered set where every element has an immediate successor, but the ordered set is not well ordered. You can consider the set of all integers in the usual order. Every integer has an immediate successor. You add 1 to that integer, you get its immediate successor in the usual order. However, it is not well ordered. Why? Because, for example, the set of all negative integers is a non-empty subset of this which has no smallest element. We have already seen before that this is not well ordered. So that is the solution. Next we have 4, and this is part A. There is another part. In part A, first the author says that this is the set of all negative integers. Okay, some notations, z minus. And it's also assumed to have the usual order, that it inherits by being a subset of the ordered set of all integers. Okay, so it's the usual ordered set of all negative integers. Now we have to show that a simply ordered set A is an ordered set, will not be well ordered, will fail to be well ordered if and only if A has a subset which has the same order type as this. Okay, so this is an if and only if statement. So we have to go both ways. Let us first solve this and then we will see part B. One half of this if and only if claim is quite easy. And it is this half where we assume that A has a subset B which has the same order type as the ordered set of all negative integers z minus. And we have to prove that in this condition A is not well ordered. Suppose forcefully that A is well ordered. Now B, of course, is a subset of A. Additionally, B is non-empty. Why? Well, because B has the same order type as the set z minus, and z minus is not just non-empty, it's actually infinite. So as such, B is also infinite actually. We, however, need non-emptiness here. So B is a non-empty subset of A, and because our supposition tells that A is well ordered, so B will have a minimum element. But because ordered theoretically, B is actually nothing but z minus. So accordingly, z minus also should have a minimum element, and that too in the usual order, which is clearly false. There is no smallest negative integer, and that's a contradiction, and that is why our supposition is wrong. So A cannot be well ordered. Now we go for the converse. Conversely, let A be a set which is not well ordered. Okay. We then have to prove that A has a subset whose order type is the same as the set of all negative integers. This one is a little complicated. I mean, it's not as easy as that other part. But anyway, let's see how it goes. Because A is already an ordered set but is not well ordered, so every non-empty subset cannot have smallest element. There is at least one non-empty subset which has no smallest element. Otherwise, they will be well ordered by definition. Let C be such a set. There may be multiple such sets. C is one of them. So, C is a subset of A which has no smallest element, and this is a direct consequence of A not being well ordered. Alright. Now, for every C belonging to C, that means this is an element, we define SC, which is the set of those elements in C which are less than that C. It looks like the section of C. You may call it that. However, do not forget that sections have been defined only in well-ordered sets. We are not in a well-ordered set exactly right now. But anyway, we can use the notation SC. Now, the fact that C has no smallest element makes each such SC non-empty. Why? Well, suppose SC is empty for some C, for some element C. What will then happen? Then on that side of C there is nothing. Nothing where? Nothing in this C. But then that makes that C the smallest element of capital C, which is what capital C does not have according to our choice of C. And that is why each such SC has to be a non-empty set. And each SC of course is a subset of C. So, we now have a collection of non-empty sets. For each C in C, we have this non-empty set SC. So, this is a place where we can use the axiom of choice, which tells us essentially that from each SC we can choose one element, we can pick one element. And there exists a function that helps us do that. That function is, say, f. So, f is a function whose domain is the collection of all those SCs, and this other set is the union of the SCs. You go back to the section where axiom of choice is discussed, there you will see that there is a lemma there. I think it's lemma or theorem, I don't exactly remember, which tells us that such a function exists. It's called a choice function. What is the property of this function? The property is that you see the inputs of the function f are the sets SC, and the outputs are elements, after all elements in this union, which means elements in C after all. And the property that f has is that f of SC, that element of C, belongs to SC. Okay, so there is no point discussing about what axiom of choice means here, because that's not our aim here. So we now have a function f like this. Now how can we use this f? Let's see. Okay, so after having that f, next what we do, we choose any element C1 in C. That we can of course do because our set C is non-empty. And then by the principle of recursive definition, there exists a function which is a sequence actually, a sequence of elements in C, and that sequence is the H. Okay, there is a very big storm going on outside. I don't know what's happening with these storms. It's pretty big. Okay, but let's not concentrate on that. So this H has the set of positive integers as its domain. So that is why it's a sequence, and it's a unique function with these properties. H of 1 is that chosen element C1, and H of I for higher values of the input I is f of S H of I minus 1. Does it make sense? You see, the function H after all takes its outputs in C. So in particular, h of I minus 1, the previous h value before h of I is an element of C. So for that element we can consider that section type of steps S h I minus 1, and on that we can apply our function f, for which the inputs were those steps SC. So this way we get a legitimate function, and there is actually only one such function which satisfies these conditions. Now we will use this function h to create that subset of our set A that we are looking for, which will have the same order type as the set of all negative integers. Let's see how. Okay, so the candidate for our subset of A, which should have the same order type as the set of negative integers, is this. Okay, and it makes sense also because this h of z plus will be a subset of C and accordingly a subset of A. And for that purpose we have set up a function also g from z minus into this. And the definition of g is this: g of x is h of minus x. Let us see if it makes sense, if g is well defined. You take any input from here, so x is a negative integer, and that negative integer, when you take its minus, it turns into a positive integer, and when you evaluate h at that positive integer, you get an element of C. In particular, that element of course is here, and that's a unique element because h is well defined, and that is why g is well defined. However, before we say anything more about g, let us also note this property that h has. For any positive integer I greater than 1, h of I is less than h of I minus 1. Why? Why is that so? You recall what the property that this function f has. Remember, f has this property, no? F of ST belongs to ST. Now what does it mean for something to be in this set ST? It will be less than C, and as such f of this will be less than this thing. But f of this by definition of h is h of I, so that's how we have this thing. Okay. Let us now go back to the properties of G. We have already shown that G is well defined. Something else also you can say immediately about G, which is that G is surjective, G is onto. Why? Well, you take any element from here, that element will be h of something. What is that something? That something is a positive integer. Say like this, you can take, say you take y in h of z plus. Okay, then by definition of this, y will be h of z, where z is some positive integer. So you can then write it as minus of minus z, where minus z now is a negative integer. So by definition of G, this will be equal to G of minus z. And that's how any element in this set is the G image of some element in this set. So that makes G onto. What else can we say about G? Okay, so we first write these things about G that we have seen just now. Clearly G is well defined and onto. Next we go for one-to-oneness and order preserving nature of G. If we can show that G is order preserving, then automatically it will be injective, one-to-one. So for that we take any two elements in the domain of G, x and y, with x less than 1. Then you look at this chain of inequalities. You start with G of x, that by definition is h of minus x, and now you use these inequalities here. So you subtract 1, you keep subtracting, you get higher and higher h values. Because x is less than y, so I mean you have to manipulate the inequalities a little, okay. Because x is less than y, minus y is less than minus x. So if you, you can write minus x on this side and minus y on this side. So if you keep subtracting 1 again and again from minus x, it will go towards minus y. So that way, and at every stage we will have higher and higher h values. So that way we first go from minus x to minus x minus 1, and then eventually we reach minus y. These intermediate things may or may not be there, okay, depending on how far minus x and minus y are from each other, but just write generally like that. So that way we get h of minus y, which by definition is g of y, and that is why g is order preserving. If x is less than y, then g of x is less than g of y. So g is order preserving and hence injective. Why? Because distinct inputs have given us distinct outputs, and that is why g is injective. So g now becomes a bijection which is also order preserving, and as such, because g is a function between these two sets, as ordered sets they are of the same order type, and that way we get this subset of our original set A which has the same order type as Z minus. Okay, so that is the solution to part A. Next we have part B of 4. Here we have a simply ordered set A in which every countable subset is well ordered. Then we have to prove that the entire set is also well ordered. Now the fact that we have part A, it's very easy to prove this. Let's see how. Okay, so this is the solution. We have to prove that our set A is well ordered. Suppose it is not. Then by part A, there exists a subset of A, let's call that C, which has the same order type as the set of all negative integers in the usual order. But being of the same order type as this set, in particular also makes C have the same cardinality as the set of all negative integers, because there will be an order preserving bijection. So there is after all a bijection, and this is a countable set, a countably infinite set in fact. Accordingly this also must be countable, but then by our hypothesis C must be well ordered, okay, because every countable subset of A is well ordered, that is given. But then the corresponding other set, Z minus, which in a sense is nothing but C itself, only its elements are labeled differently, must also be well ordered in the usual order, which is false, because this is not well ordered, and that is why our supposition is wrong. So A must be well ordered. So that's the solution. And let's just end the video here itself. Tomorrow I think we have class 11, class 12 exercises are there, I think. So let's do class 12 tomorrow. So see you tomorrow with that. Until then, this is me, Lucifer from A Mathematical Tool. Have a nice day.